Tsinghua University. He also has served as a senior engineer at LCD Technology AU Optronics. He was also a postdoctoral fellow at National Tsinghua University. His field of studies are nanomaterial growth and device design, electron beam lithography, organic inorganic hybrid solar cells, optical film simulation design, and he have his own nano optoelectronics laboratory at National Taiwan University of Science and Technology. We welcome you, sir, and you all will get the benefit of today's lecture. Thank you.
Okay, thank you to the nice introduction from Dr. Pradeep. Pradeep. Okay, I will correct that later on. Okay. Okay, so good afternoon. Okay, good afternoon. And I noticed that some of you from the IATP program and some of you from GDIP program. Okay, how many of you have already taken my lecture in material science? Okay, yeah, mostly local students, I can understand that, okay? And yeah, we will see for 4 hours today, right? I will see you for 4 hours, okay? It's a long class. So I will try to make this one short, okay? This is a brief introduction of our department, okay? As you can see, I belong to the Department of Material Science and Engineering. So I'm here today to provide you a department overview, okay? And hopefully that for the IATP students, you may feel quite unfamiliar with our department, okay? Because I've been to some other countries, okay? And in many countries there's no such thing as material science and engineering, okay? And so apart from that, some of them belong to more like metallurgical science and engineering, right? Okay, so I think this is based on the development of or culture of different countries, okay? Because in Taiwan, we currently focus on the semiconductor industry, okay? But for some countries in like Europe or like even in America, okay, the semiconductor fabrication or the semiconductor industry is more related to like research and development. Okay, so there are not as many workers needed in the semiconductor processing industry. Okay, so that's why you see that almost all of the universities in Taiwan has material science and engineering. Okay, and over like 85 to 90% when they graduated from master, they joined the semiconductor processing industry. Okay, so if you feel that later on you will be interested in working like in the semiconductor related industry in Taiwan, maybe you can consider taking some of our courses. Okay, that will we will try our best to prepare you as a talented researcher or engineer in the related industry. Okay, and my name is Mo-Lin Tai. I'm currently an assistant professor in the department, and later on I will also briefly introduce some of my research. Okay, and at that time I have a CV page to introduce more about myself. Okay, but first we start with the department overview. Okay, so the outline of this overview can be separated in 5 parts. Okay, the first one will be a brief introduction of our department, and the second one will be the research, including all the professor faculties in our department. And for part 3, I will focus on the courses. That will be, I think that will be the most important for most of you, okay, since you are all undergraduate students. As long as you, only if you like doing a project in a lab, you will care more about research. Okay, most of you will still pay more attention about the courses. Okay, and actually, there's one thing before I start. Okay, I can allow you to write your notes during my talk. Okay, so 可以考虑一下看，不要这样。Okay, so you can save some time. You don't need to wait for me to finish my talk to write it down. Okay, maybe I can also tell you some of the important things. Okay, maybe about courses during my talk. Okay, and part 4 will be research environment, mostly about the facilities in our department, and part 5 will be about career development. Okay, as I said, most of the students will study master. Part of them study in local graduate institute, and part of them go abroad. Okay, go to another country to study either master or PhD, and then eventually, I think over 80% will go to the industry, 80 to 90%. Okay, so the first one will be introduction. Okay, so actually, our department is a very old department. Okay, this is the year the NTUST was established. Actually, I'm not quite sure about that, but I think our department is one of the 4 original department. Okay, original means at that time, NTUST established. We already have our department, but at that time we don't call our current name. Okay, at that time our name was Department of Textile Engineering. So you know, the name of the department are closely related to the industrial development, right? Okay, because at that time, the mainstream of the industry may be more related to textile engineering, right? Okay, and then later on, we changed the name to fiber engineering. Okay, it's more about clothes, right? Okay, try to make different colors in your clothes. Okay, so you need some like a some courses related to how to dye. Okay, the dye means 染料. Okay, not the dead. Okay, it's dye related techniques, right? Okay, so it's called the fiber engineering. Okay, and at that time we started the master program. Okay, and the PhD program was started from 1985, and then at the year 2000 we changed the name to Fiber and Polymer Engineering. So you see, if you want me to tell you what's different between our department and other material science department in another university in Taiwan, is that our department has more polymer related research. Okay, so if you're more interested in the organic synthesis, organic material synthesis, or polymer related research, okay, there's you may want to talk to some of our professors in the polymer related research field. Okay, and 2003 we changed to polymer engineering because I think most of the fiber related company went to like mainland China or other countries. Okay, so and at 2005 we started our international program. We started to recruit international students, mostly master student and PhD student from the mostly southeastern countries, Southeastern Asian countries. Okay, mostly from Indonesia. Hello. Okay, mostly from Indonesia, Vietnam, and India, and some of students from Ethiopia as well. Thank you. Yeah, I can use this for now, okay. And in 2010, we changed to our current name. It's called the Department of Material Science and Engineering. Okay. Yeah, I will go on to talk about that. Okay, so currently we have 19 full-time professors and 5 associate professors and 6 assistant professors, including me. Okay, among them, 4 of them from Taiwan and 2 of them are foreign project assistant professors. Okay, 1 from India and 1 from Indonesia. Okay, and we have 2 lecturers mainly in charge of the lab-related courses. Okay, and we have 9 staff in our office. Okay, and the number of students in 2022 will be about 700, right? Okay, 400, almost 800, 440 from the undergraduate and 358 in studying graduate program. Okay, so let's go on to talk about the research part. Okay, as I talked about earlier, we have 3 different research divisions. Okay, one of them was organic materials. Okay, so there's still some, like 1 or 2 professors working on fiber engineering. Okay, due to the historical issues, right? But later on, we will still recruit some professors with. We still need some professors from fiber-related techniques. Okay, and most of the new professors work on either polymer-related electronics or biomaterials, including bio engineering and like wearable devices. Okay, for the bio-related applications. Okay, and we have 4 professors working on material processing. Okay, and 2 of them are more related to mechanical engineering. It's about like the automation systems. Okay, automatic process. Okay, and then 1 of them more related to the organic material processing, and 1 of them more related to the inorganic material processing. Okay, and the 3rd division in our department is the inorganic material division, and this is more like the traditional material science department, including research fields related to metals, ceramics, and semiconductors, and nanotechnology. Okay, so I'm also one of the members in the inorganic materials. Okay, but since the integration of research field is quite important nowadays, okay, even I am in the inorganic material division, I still do some organic related research. Okay, so there's actually not much difference between, there's not a clear gap between them. Okay, so integration is quite important. Okay, so first of all, I would briefly introduce the organic division. Okay, so we have about 10 professors from the organic division. Professor Yang working on biomedical devices. He has some project related to the contact lenses. Okay, the glasses, right? The invisible glasses that you wear in your eye. Okay. And Professor Hong worked on the soft matters or functional gels. And Professor Chen mainly worked on the organic-related semiconductors, okay? Organic-related semiconductors. And Professor Chen Zhijian, our former chairman, worked on the organic synthesis, okay? Actually, their research field are too difficult for me, so most of the time, I don't know what they are talking about during their presentation. Okay, but if you're interested, you can go to them to have a further discussion. And Professor Wu worked on the nanocomposites.
And I think he also works on the more novel piezoelectric nanogenerators. That's for the wearable devices, so you don't need additional batteries. Okay, if you try to develop some smart clothes, okay, smart clothes, 智慧衣, okay, so that you can use the piezo nanogenerators, okay, that can generate electricity automatically without the additional batteries. Okay, and Professor Yu also work on the organic solar cell and organic related devices. Professor Ye work on the micro and nanocellular foam, and Professor Zhang working on also the organic related optoelectronic materials, including solar cells and piezoelectric devices. And also Professor Xiao worked on the organic electronics, including organic bioelectronic medicine devices. And also Professor Lai, he has many projects collaborating with hospitals or researchers from the academia sinica. Okay, and his English is very good because he was formerly a professor in the University of Washington in Seattle. Okay, he just came back like 2 years ago. Okay, so he's like more like a native English speaker here. So if our department needs some like technical English classes, he's willing to help. Okay, so I think he also offered the course in the GD program. So later on, you may take his course in your department. Okay, and Professor Zheng is our vice chair currently, and she works on the drug carriers. Okay, so she also has some project with hospitals. And Professor Lin mainly focus on almost all the professors I introduced before focus on experimental science or technology, right? Professor Lin is quite unique because he works on the simulation, okay, computational calculation. So his research field is including like quantum chemistry, first principle, and molecular dynamics simulation. Okay, so that's all for the, oh, there's another one, okay, our new, young, beautiful, pretty Professor Luo, okay. She works on advanced polymeric synthesis, okay, also related to organic optoelectronics. And the second division will be the processing division. Okay, there are 4 different professors, including Professor Guo and Professor Huang. They both work on the design of control systems, so it's more related to the mechanical engineering. Okay, and Professor Ke works on the LED development. Okay, so it's more like I think organic material. And Professor Cho works on the polymer-related research. Okay, and the last division that I want to introduce is the inorganic division. Okay, the inorganic division, Professor Zhu worked on the metallic glasses. Metallic glass, that means amorphous, non-crystalline metals. Okay, it's not a glass. Okay, it's metals instead. Okay, and Professor Guo works on the electrochemistry related research. Okay, including the catalysts, in green redox reaction. And Professor Yan worked on the metallurgical thermodynamics. If you join his lab, he has some collaboration with the industry in the United States related to the metallurgical thermodynamics calculation. Okay, so if you want to participate in some intern program in the United States, you are welcome to talk to him. And Professor Zhou worked on the semiconductor manufacturing.
Okay. And Professor Professor Chen is currently the leader for the precious system, precious system office in our university, 贵重仪器中心主任啊。So she's mainly in charge of all the precious instruments, including like a transmission electron microscope or the SEM scanning electron microscope and XRD. Okay, so if you're interested in operating those, the price of TEM in our university will be about 60 million NT dollars. So it's like I don't know, 2 million US dollars. Okay, so if you want to have some chance to use that kind of a system, you can talk to her. And then Professor Wang Tenhao is currently a vice dean in the College of Engineering. Okay, and he is quite famous in the fuel cell and the energy-related devices. Okay, so if you're interested in those energy storage devices, you can talk to him. And Professor Shi is currently our chairman, and he's mainly focused on ceramics. Okay, and he graduated from University of Oxford. Okay, so if you're interested in studying University of Oxford, okay, he's very eager to send his student to the United Kingdom. Okay, if you're interested in study there. Okay, and Professor Wang was my senior back in the National Tsinghua University, and she works on the fabrication of nanomaterials, including mostly related to nanowires. Okay, architectural growth of nanomaterials and the growth of nanowires, and also some nano devices based on nanowires. Okay. And then this is me, okay? I mainly work on playing tricks. Oh no, not playing tricks, okay? I mainly work on the growth and design of two-dimensional materials or quantum dots, okay? Two-dimensional. So Professor Wang was more related in one-dimensional nanowires. I work on 2D and 0D, okay? Because I don't want to fight with her, okay? And Professor Liang is more related to the metallic materials. Okay, so if you're interested in metallic material, you can go find Professor Liang, Professor Yan, or Professor Zhu in the previous pages. If you're more interested in ceramics, you can go find Professor Shi, our chairman, and Professor Guo also did some ceramic-related research. If you're more interested in going to UCLA, you can go to Professor Zhou's lab because he just sent a student to UCLA whose GPA is like a normal, not quite good, but still goes to UCLA. Okay. Okay, and these are our two lecturers, mainly in charge of the laboratories. Okay, so we have in our department we have 5 lab courses, okay? And the first 3 classes or courses are required courses, and Lab 4 and Lab 5 are elective courses, okay? And Professor Huang also graduated from our department, and she supports a lot in the international graduate student admission in our department, okay? And these are the 2 foreign project professors. Professor Harris, I think some of you took his calculus, right? Anyone take his calculus? Raise your hand. No? Okay, maybe there's some conflict in the courses. Okay, I don't know. Okay, he offers calculus 1 and calculus 2. Okay, and he's from Indonesia. Okay, so for Indonesian student, you can also find some chance to know him. Okay, he's a very kind person. He supports a lot in the life of an Indonesian student, and he also has some collaboration with me. And also, this is I call him AK. Okay, Prasanna. Okay, AK, and he's from India. Okay, so if there's any Indian student here, you can like find him. Okay, and he mainly teaches chemistry. Okay, so if you're interested in because he's from the polymer organic related division, department. Okay, so his courses are more related to chemistry and polymers. Okay. Okay, so let's get to the point directly. Okay, about the courses and facility. Okay, this is part 3. Okay, so I think for the first year, there's nothing to talk about because these are all required courses, okay? And I think for chemical and material science major students, you take material science course, right? Okay, from Professor Deng's class, right? So how many of you take the material science? Can you raise your hand? Only a few, okay. Have you already decided you want to select which major or not? Not yet. Sorry? Nothing, okay. Okay, so yeah, later on maybe you can think about after I introduce the rest of the year's courses, okay? This is the freshman courses, okay? You have Material Science 1 and Material Science 2. And for starting from the second year, okay, you can see there's some difference among all the majors, okay? For example, for our material science and engineering, okay, we focus on the organic chemistry. For engineering mathematics, I think all 4 majors, you don't have a choice, right? All of you need to take engineering mathematics, okay? And for the chemical and material science engineering, we both need organic chemistry, so you don't have a choice, okay? But if you are not feeling comfortable in like a material and engineering balances or unit operation, okay, you are always welcome to join our major, okay? The material science and division lab, okay? The lab will make you feel more relaxed, I think, okay? And all of them needs programming language, okay? And you see we have a choice, but I don't know why. I think all of you should have choice, so I'm not sure. Maybe they will update their courses later on, okay? And the one thing about the core course in material science is the thermodynamics of materials, okay? So you may want to, when you take the material science course, there's one chapter more about the thermodynamics of material, okay? About the phase diagram, okay? Probably chapter 10 or chapter 11, okay? If you think that's quite interesting, okay? Or you don't feel like you don't know what it says, okay, you can try to select the material science major because this course is just the extension of that chapter, okay? All of the core courses are all slightly covered in the material science course, okay? So you will feel like more comfortable because it's just like a review, okay? So that's my point of view, okay? Thermodynamics of materials. And there's also the polymer material introduction in the material science course, right? Okay, so the extension will be the introduction to polymer systems. Okay, it's about the properties and the fabrication techniques and physics of the polymer related materials. And the kinetics and phase transformation of material are also already covered in the material science, okay? So there may be some, we go a little bit deeper into that chapter, okay, to talk about the diffusion of atoms when you have 2 different materials mixing together. Like atom A will diffuse to the atom, the region A, atoms from region A will diffuse to the region B, okay, something like that. You try to do some, to form some models for the calculation, okay? And the phase transformation of material are more like if you try to heat the gas to a high temperature and you cool it slowly, it becomes more crystalline. It becomes something more like glass ceramics, okay? If you cool it fast, it becomes amorphous, okay? It becomes glass, okay? And optical properties may be slightly different, okay? So that's more related to the kinetics and phase transformation of materials. And for mechanics of materials is more related to, I think, mechanical engineering. Okay, you try to calculate the loads or the mechanics when you have like a different composition of materials. Okay, yeah, that's the courses we had in the second year. Okay, for juniors. Okay. The junior should be third year, okay? Second year is sophomore. For the third year, we go a little bit deeper into the properties of material, which also cover in material science 2, okay? Material science 2, there will be some main topics including thermodynamics and kinetics, okay? In Chinese, we say 动力学跟热力学 that are the main topics of material science. Okay, apart from that, we also study what? The physical properties. But the physical properties here is not related to mechanical properties. Okay, it's more related to what? To the electrical, magnetic, thermal, and optical properties. Okay, so you can like check the later chapters in the material science textbook and see if you're more interested in the physical properties of materials. And there's one main topic is about the introduction to X-ray crystallography and diffraction. Whenever you do research, you need to use XRD for the examinations of your material structures, okay? And so this course, many students from other departments will also come to take this course. You know why? Because this course, only when you take this course, okay, you are qualified to use the XRD. Okay, so every year, like more than 100 students, okay, take Professor Shi's course in the XRD. Okay, and we have another lab course. Okay, lab 2, okay, material science and engineering. Okay, and this one is elective. Okay, for those of you more interested in polymer chemistry, you can take this course. And then characterization of materials will be more related to other kinds of material analysis, including like TEM, electron microscope, or like Raman or PL. Okay, that kinds of characterization tools. Okay. And since most of the students who graduated will join the semiconductor industry, okay, there's a course related to physics of semiconductor materials. Okay, I think next semester will be offered by me. I also offer the physical properties of materials for the juniors in the IATP and GDeep. Okay, I think like a large amount of students came every year to take physical properties of materials. Okay, but currently there's only one student in the junior year. Okay, take the physical properties of materials. Okay, but in the second semester, okay, he will also take the physics of semiconductor materials. Okay, there will be another lab course. Okay, the first lab course will be more related to the metal processing. And we try to observe the grains and grain boundaries in our metals, okay, metals. And the second lab course will be more related to the ceramics and polymers. And third lab course will more related to the electrical characterization of materials. Okay? And the fourth year will be a quite easy year, okay? You just need to do project, and then you can select whatever course you want, okay? I think there will be no required course apart from the project. Okay, so that's all about the courses, and then I will go on to briefly talk about what the material science is about, okay? But I will not go very deep, just to let you have some brief understanding, okay? On the left-hand side, you can see we have Coke bottles, right? Okay, you can see that using different kinds of material. Why do I say different kind? Because at the top, you can see aluminum can. That's a metal, right? And on the center, you have ceramic bottles, glass, okay? And at the bottom, we have polymer, right? PET, okay? And then in material science, we're also interested in using the same element, carbon, right? But by orient the carbon atoms in different way, you can see it can become graphene. Graphene is a conductor, okay? And if you try to make it into a tube, it becomes a semiconductor, okay? And if you try to let it oriented in a three-dimensional way, it becomes diamond, which is very strong and has mechanical properties, but is insulator, okay? So that's a different thing you can play with using the same element. Okay, and we also want to understand the structures of material. What are the different structures? For example, this is a base center cubic, okay, and there are all other structures, okay, and the defect. Defect is quite important when you go to semiconductor processing, okay, because by controlling the conductivity of semiconductor, you are actually trying to induce some defect, okay, you try to induce some substitutional atoms, including, so the additional electrons will change the electrical properties of your material, okay. We also try to compare the mechanical properties of materials, okay. So we identify the different strengths or toughness, or to evaluate whether it's a ductile or brittle materials, okay, to do the material analysis. Okay, we also focus on the failure mechanism of materials. Okay, there are many interesting or disastrous stories behind it, right? And by the end, people will want to know what caused these disasters to happen. Okay, sometimes it's quite fortunate, okay, because I think almost all the passengers on top of this plane survived, okay, this incident, okay? And we also try to understand the processing techniques, how to make your material into the form you desire. Okay, and that's what I talked about, the kinetics and diffusion. I think in the this is in the chapter 5 of your textbook from material science, okay? And these about diffusion of atoms, and this about the thermodynamics phase diagram, okay? So we want to understand that a certain composition, okay, you can see. Normally, back in the high school, we said that we only care about the liquid phase, gas phase, and solid phase, right? 3 different phases, okay? But actually in materials, especially in solid, in like a steel, okay, there are a lot of phases, okay? All of them are solid, okay? But by introducing different composition of carbon, okay, you will see different mechanical properties, different melting point, okay, or different mixture of crystal structures, okay? Okay, so later on we'll go to understanding the physical properties of materials, including the electrical properties, magnetic properties of materials can be used to design like a electron microscope. Okay, you can try to focus your electron beam. Okay, and optical properties can be used to design some light emitting devices. And this is also an example from our lab. Okay, we try to use quantum dot. Quantum dot. Some of the quantum dot are like luminescent materials. 它会发荧光 luminescent materials. Okay, so you put it under the UV light, there will be light conversion. Okay, you can change the UV to green light emission. Okay, and you use an inkjet printer. 用喷墨印表机 inkjet printer, you can print out the word you like. You can print a QR code. Okay, to make it luminescent under the UV light. Okay, which is quite interesting for the undergraduate students. And this is the thermal properties of material. We try to design a heat shield for the spacecraft. Okay. Okay, and these are the material analysis facilities. Okay, here this is a TEM. This is the one I said is like 60 million. Yeah, 60 million NT dollars. Okay, 2 million US dollars. And this is scanning electron microscope. I came to the NTUST at 2018. Okay, this one was bought like around 2020. Okay, so it's younger than my time in NTUST. Okay, quite new one. And for this one, you don't need to stand beside the TEM. Okay, there's another computer in another room. Okay, so you just need to put your sample inside and you go to another room to do the operation using the computer. Okay, so it's more advanced TEM. Okay, usually we need to like sit beside our electron microscope. Okay, and then try to do some adjustments, right? Okay, but later on it's all highly automatic. Okay, highly automatic. You just need to control the computer. Okay, and this is the XRD, and this is AFM to do some. If you have like for example 2D material. 2D material means you have like an X and Y in large scale, but in the Z-axis, the height of the material is only several nanometers. Okay, atomically thick. Okay, so you need to use some probes in order to measure the height. Okay, and you can also change the probe. Okay, if you change it to a conductive probe, you can measure the current at a certain region. Okay, if you change the probe into a magnetic probe, you can analyze the magnetic properties at a certain region. Okay, so this is quite useful if you want to understand the microscopic physical properties of materials. Okay, and these all facilities are in the Engineering 1 building. Okay, E1 building. E1 building, half of the E1 building belong to the material science department, and half of the E1 building belong to the mechanical engineering department. Okay, and these are all located on the material science sites. Okay, since mostly the PIs, okay, project instructors, are in charge of these facilities are from our department. Okay, and we also have some courses. These are graduate courses, okay, but if you are going to your junior or senior year, you are able to select those courses, okay? And mostly we will invite lecturers from like a TSMC or SMOR or the Applied Materials and so on to talk about the latest advances, okay, in the semiconductor processing materials and techniques, okay? And that includes the device design, Okay, for example, previously we have planar FET, and later on, in order to do the scaling of the devices to reduce the size of a single device, okay, we try to make it into a FinFET. Okay, FinFET is quite popular in the semiconductor related applications to better control the channel of the device, okay? And later on, people are actually working on making the multiple channel gate-all-around devices. So will be the next step in the next generation of the device fabrication. And also, previously people use 2D to do the packaging, okay? And the newest technology use 3D IC to do the packaging, okay? This can largely increase the density of the device within a certain area, right? Later on, before we use 2D, so we need a large area. Now we can stack the ICs, okay, to increase the device density. Okay, and also the processing techniques. I think most of you have heard about the EUV, right? Okay, so we have lecturer from the industry talking about the lithography. Okay, lithography, etching, and diffusion, and also the ion implantation. Okay, and we also have some, these are the pictures of the lecturer. I think he's a manager from the Applied Materials. Okay, and this one is one of my former colleagues when I was in the Academia Sinica. He was working in the ASML in Netherlands. Okay, but later on he came back to Taiwan and started his own company, okay, called Redefine Innovation. And he's currently providing some consulting for the semiconductor related companies. Okay, he opened some workshops or international conference doing some services for them. Okay, he also has some research and development collaboration with our university. Okay, and we also had some internship opportunities. Okay, but mostly I see local students go to the internship. Okay, but I already talked with some of the companies. For example, if you go to Garmin, maybe there will be some internship opportunities for the foreign students as well. Okay, but for these foreign companies, maybe you need to apply online first. Okay, after they accept you, then this can also count as your credit. Okay, there are two kinds of internship. One is the summer internship. It counts as 3 credits in our department. Okay, and for the semester internship, counts as 9 credits in our department. Okay, but for the semester internship, there's a restriction that you cannot take other courses in that semester. Okay, so mostly the people go to semester internship are all senior undergraduate students. Okay, and the internship opportunities are not limited to these companies. Okay, there are still other companies available. But if for the companies not listed, if you want it to become your credit, then we need to sign a contract between the department and the company. Okay, only when we sign a contract, and I will visit these internship companies during your internship. Okay, like for new company, I will visit once. Okay, I will visit twice. One, first to see the company, and second during your internship to talk with them. Okay, and for the companies we already had, okay, I will visit once during your internship. Okay. Okay, so I think time is up for the first hour. Let me have a 10-minute break. Okay, I will continue to do it after 10 minutes. Okay. I met a student downstairs. Okay, later on we'll discuss with him about the related courses. Okay, and let's go on to talk about the research environment. Okay, it's more like facilities, but I would just list it out all the labs we had. Okay, previously it's about courses, courses related to those precious facilities. Okay, now it's our labs. When you're doing research, you may need to use some facilities. Not all of them are precious instruments. Okay, but still useful. Okay, for example, the materials chemistry lab, you can do some chemical experiment in the hood. Okay, and also for the high temperature materials lab, there are some furnace. If you need to do some high temperature processing, okay, you can go to borrow the high temperature furnaces from the public lab. Okay, I think for this lab is also available for the students in another department. Okay, not limited to the material science department. Okay, but the cost will be slightly different. Okay, maybe it will cost more for the students from the other department. But as long as your professor can pay the bill, I think everything's okay. We're fine with that. Okay, and yeah, and also some TEM, XRD, and FIB, just like I talked about. The focus ion beam is this one. Okay, this can be used to do some ion meeting. Okay, if you want to do some microelectronics, sometimes you need to cut some channels. Okay, on your substrate. Okay, that way you can use FIB. Okay, normally it's used to prepare the transmission electron microscope samples. Okay, why? Because usually for TEM we cannot allow samples that's too thick, because you use the electron beam. If your sample is too thick, since it's a transmission electron microscope, the electron can no longer transmit through your sample. Okay, so we want to make our sample as thin as possible. Okay, so we need to use the FIB to cut a small piece of our sample in order to do the analysis. Okay. Okay, and there are also some 3D printing labs. Usually the students from the mechanical engineering department will come to use that. Okay, because for these labs, if you want to do a project related to 3D printing, you need to use the software to first draw out your ideal model, right? Okay, you need to first draw a figure. Okay, using the modeling tool. Okay, and then you input the figure or model or the CAD file, okay, CAD design file, into the 3D printer, and the printer can help you to print it out. Okay, and this lab is actually an official lab for the government qualified. Okay, if you want to prepare for a 3D printing professional certificate, okay, you can apply for the qualified. Okay, and this is the test area. Okay, the area that's for the test. Okay, 检定考场啦. Oh, okay, so you see many 3D printing, but they all look the same. Okay, because we need that many for the qualified. Okay, and we also have a laser cutter. Okay, if you have some wood, you want to design your own logo. Okay, you can go there, and then you still need to draw a CAD file and input into the laser cutter. Okay, and it can be used to design your own logo. Okay, and there is also some discussion area. Okay, so if you belong to a lab, but there are too many students from your lab, okay, some students just go to the discussion area, and this becomes his own workspace. Okay, and the last part would be about career development. Okay, career development. I have updated the numbers from 2022, okay? So most of the students graduated from our department will be either study in the local graduate institute or study abroad, okay? Mostly, like almost 70% will study master at least, okay? And about 3% will go abroad, okay? And 17% will go directly to work, and for local students, 4.5% go to military service, okay? And for others, maybe they want to go into a government department, okay? They want to prepare for the test, okay? 国考, okay? They will prepare for the test to get into the department, okay? And some of them prepare to go abroad. Okay, not study abroad directly, but they prepare their like TOEFL or the GRE for the studying abroad. Okay, so I think that's all for the department introduction, and I will briefly introduce some of my research topics. Okay, just in case if you're interested. Okay. But currently, I already had like 10 project students, okay? I think 4 from the material science and 4 from the GDeep and 1 from IATP, okay? So maybe if you're interested, we can discuss about that later on, okay? Next year at least. And my research will be more focused on the quantum dot and 2D materials, okay? But I can help my collaborator to fabricate those nanowire devices. For nanowire devices, we simply put a nanowire and we do some e-beam lithography. It's using electron beam to do the lithography process. Lithography means patterning. You can decide where to deposit your electrode. Okay, so you can control the pattern or the shape of the electrode for the measurement. Okay, you can try to play with the shape in order to increase the device performance, okay? And for the electron beam lithography, you can also try to design some special optical structures, including plasmonic structures, okay? And I also, during my PhD, I worked on solar cell, but recently, since I don't have some glove box or solar simulator, okay, I only collaborate with someone else to do the solar cell, okay? And since I work in the local display company before I joined the NTUST, so part of my research is more related to the display applications, okay? And I graduated from Tsinghua University, and before I graduated, this is quite unique, okay? I was actually this is a visiting student, okay? I went to the King Abdullah University of Science and Technology in Saudi Arabia, okay? You can go, if you're interested, you can go to YouTube to find this university. It's kind of luxurious, okay? But outside campus is all desert, okay? And at the main gate, there will be 2 soldiers, okay, taking a gun to protect the university, okay? So it's quite a special experience. Okay, you can go to the YouTube because in mainland China they said this university is called Tuhao Daxue, okay? So if you're interested in going to this one, okay, they have like, we have 1 TEM that's $2 million US dollars, right? Okay, they have almost 10 TEM, okay, but you can use it whenever you want because actually not so many people need to use TEM at the same time, okay? So they have a lot of oil and they have a lot of money, okay, for research. Very ideal place for research, but you can only stay in the campus, okay? But I think for like Indonesia, if you are Islamic, okay, maybe this one will be an ideal place for you because they have like a prayer room very well facilitated, okay? And but whenever I go out of campus, the only destination will be the airport, okay? Every weekend, people will go to take a plane, okay, to Europe to spend their weekend, okay? Because it's very near. Okay, it only takes like 2 or 3 hours to go to Europe. Okay, so it's very good if you want to go to Europe for vacation during weekends. Okay, and before I joined NTUST, I worked in AUO, 友达光电, okay, in liquid crystal technology department. Okay, and my research mostly related to optoelectronics, including 2D electronics and quantum dot for now. And we try to design some photo detectors. And for the quantum dot, the unique thing is that for some quantum dot, due to the quantum confinement effect, it becomes a luminescent material, okay, when you reduce the size from bulk to nanocrystals. Okay, but what's so special about the quantum dot is the emission of the quantum dot can be well controlled by the size. Okay, so if you have prepared the quantum dot in very good uniformity, then the emission width will be narrow. Okay, the narrow emission width will provide a very pure color. If you have very pure red, green, and blue, this can improve the color performance of your display because you see the triangle. The larger the triangle, the larger, the more color selections are available for your display. Okay, so some TV has already adopted the quantum dot in their backlight unit. Okay, they change their backlight to blue light and they add a quantum dot film, and it becomes very pure blue, green, and red. Okay, so the color performance can be largely improved. Okay, and recently we work on this kind of perovskite, lead halide perovskite quantum dot. Okay, and this is the synthesis. I will skip this slide. Okay, if you're interested, you can come to me. And then by tuning the halide composition, you can actually well precisely control the emission color of your quantum dot. Okay, so this can be well adjusted, and you can also use some template to make those nanocrystal form within these porous template. Okay, to well control the size of the quantum dot. Okay, but there's some issues related to this kind of quantum dot is the stability issue. It reacts quite significant with oxygen or water. And also the crystal structure also makes it not as stable. Okay, so we try to use, on the right hand side, you can see the strategies. We try to do some doping or the surface engineering method and the encapsulation method to improve the stability of the quantum dot. Okay, and this is the underlying mechanism for photo-induced aggregation. And in our lab, we may focus on synthesis of the quantum dot and do some characterization, material characterization, TEM, and inkjet printing, and to make it become powder. And we mix them with some cellulose nanocrystal to make it into a film. Okay, and we use the functionalized nanocrystal in order to further stabilize the crystal of the perovskite material. And then this is the synthesis process I will skip. If you're interested, you can come to me. And then we do some PL analysis to see the emission peak, okay, whether it's green light, blue light, or red light, okay, and also the absorbency spectrum and the XRD. And then we use TEM to evaluate the size distribution of the quantum dot. And then by tuning the halide, you can see all three colors can be well fabricated. Okay, by stacking the red one with the green one on top of a blue LED chip, we can achieve a white light LED, white light emission from this kind of composition. By tuning the numbers of films, we can go a step further to tune the color temperature of this white light. Okay, we can make it warmer or we can make it colder. Okay, and we can also try to improve the stability, okay, under continuous UV illumination, under high temperature, and under ambient condition. Okay, and another topic of my research will be more related to 2D material growth. I focus on the semiconductor 2D material that falls into the category of transitional metal ditrocarbonate, okay? Okay, but we don't use the top-down method. Top-down is the Scotch tape method, okay? It becomes like small flakes, but this is not scalable, okay? So we use CVD to try to grow a thing on top of our substrate, okay? And for the CVD, we use tube furnace, and we try to induce some carrier gas or reactive gas. And during the growth, we try to control the growth temperature, okay? You put the substrate in the downstream, okay? In the upstream, these are the precursors, and you can control the temperature to make it become gas, okay? When it becomes gas, it will be carried by the argon, and then they react within the heating zone. They react with the heating zone, and later on, after it goes to downstream, they will be deposition. There will be deposition onto the substrate, deposited onto the substrate, okay? And after the deposition, you can use the Raman to characterize your film. This is like a DNA of your material. You can use optical method to fastly characterize your as-grown material. And then you can also use PL, photoluminescence, to characterize your film. Okay, due to the quantum confinement effect, if you have a thinner film, the emission will be more significant. If you have thicker core, this is a nucleus for the growth, okay? This is thicker, so it shows darker, okay? Darker luminescent intensity. Okay, and this is related to, this is not from our lab, but our ultimate goal is try to come up with a single crystal. Single crystal means we don't have any boundary between them. Okay, why is boundary not good? Because you see this is not a single element. It's a compound, right? Okay, so if you have boundary, there may be some metallic paths at the boundary. This will lead to the leakage problem. Okay, because we want a semiconductor, we don't want it to be either become metal or insulator. Okay, and ultimately we try to come up with a nanosheet for the field effect transistor, gate-all-around field effect transistor. And this is an example from someone else. They use 2 layers of MOS2, and then they try to increase the current, the channel current can be successfully increased, okay, in this kind of scheme. Okay, and these are the lab facilities. We have a spotter, we have chemical vapor deposition system, and we have film hood, and we have chemicals, and we have snack, okay? We have snack, this is important, okay? And we have some collaborators, mainly from the Academia Sinica and NTU, NCKU, and TNU, TMU, and then University of Taipei, okay? Yeah, that's it. Sorry, it's not this from last year, so at that time it was Christmas. But now it should be like a happy moon festival or something, okay? Yeah, thank you. Thank you. If you have any question, you feel free to come forward after class, okay, for discussion.
If you have any questions? No one? Okay, then you can write your, you have,
How do you make the semiconductor to produce as a single crystal?
How can make a semiconductor as single crystal, right?
Okay, one question is how to make this Okay, this one, right? Okay, this one is quite tricky. This is actually substrate dependent. In order to make single crystal, the ideal case is you try to come up with a single crystal metal as your substrate. Okay, so for example, they use gold 111. Okay, but gold 111 is even more expensive than your like a gold ring. Okay, so this one is very expensive. But in order to make gold 111, first of all, you need to prepare a tungsten foil. Okay, and first you start with a polycrystalline gold. Okay, the polycrystalline gold can be prepared also by, for example, CVD, but maybe not this type of CVD. Maybe you need to use plasma enhanced CVD or ALD or metal organic CVD. Metal organic CVD is like you use some like a gold related organic compound. You use some like organic material, but it has gold. Okay, and you try to control the temperature that gold will be detached from the organic molecule. Okay, and then eventually they will like be deposited onto your substrate. Okay, and then you need to do what? Annealing. Annealing means you need to heat up your sample all the way to 150 degrees. Okay, under that temperature, it will be like a half melted. It will be reorganized in a more periodic, orderly manner. Okay, under this high temperature. Okay, but under this condition, maybe you also need to control the atmosphere. For example, I'm not sure about that. Maybe we need to check the paper. Okay, sometimes we need like a high vacuum. First, you need to evacuate your chamber, and then you need to anneal under high vacuum. Okay, in order to be deposited or arranged in a more orderly way. Okay, after you eventually successfully deposited gold 111 on top of tungsten, then you try to use the CVD. And since due to the lattice match between your substrate and your MOS2, it tends to arrange in the same direction, right? You see these crystals all arranged in the same direction. Okay, by controlling the time, you will be growing into the film. Okay, so if it's grown in the same direction, along the same direction, then if it grows to a film, then there will be no boundary between them. Okay, so this is quite critical. It's not very easy to achieve. Okay, but I can tell you that the substrate is very important during the growth procedure. Okay, you need to select the appropriate substrate. Okay, and I talked about lattice match. Lattice means in the last hour I talked about the crystal structure, right? So different material has different width or length or height in their crystal structure. Okay, you need to select, for example, the MOS2 and the gold 111. 111 means a certain plane of the crystal. Okay, facing upward. Okay, certain plane is like a 111 plane. Okay, and if the gold is arranged in 111, okay, then the lattice between your MOS2 and the gold is close, so that once you have MOS2 deposited on top of gold, they can identify each other. Okay, so they will automatically arrange in the same direction. Okay, so in our lab, it's not that successful. Okay, usually it's randomly distributed. Okay, but this is one of our goals in the future. Okay.
Anyone else?
Yes.
Thank you for the speech. And you have mentioned collaboration or cooperation company that we can work on intern in our senior or after we graduate. So I want to ask you about the chance of turning material science into business, the opportunity of turning it into business.
Turning material science, you mean open a company on your own, or you join another company?
I think like using our skill in order to join the business industry.
Okay. Actually, if you can come up with this one, okay, TSMC will be very interested in buying your like patent or your research result, okay? Because why? Because you see that for the semiconductor industry, currently we are at this stage, okay? So people try to find out a more cost-effective way to achieve this multiple gate-all-around using multiple channels, okay? And why do I talk about this? Because this is one of the ways to achieve this, okay? So TSMC even has one of its department working on this type, okay? But this hasn't been mass-produced as a commercial product yet, okay? So I think this is one of the chance if you're interested in the semiconductor-related technology. And for this, okay, for example, why I am interested in this research, okay, because you see, here, Samsung, right? Okay, Samsung, they decided to use indium phosphate, okay, quantum dot in their display. So they compare with OLED. Okay, the QLED TV shows the better color performance, right? Okay, but you see, the Samsung indium phosphide, the quantum yield is still low, right? And the emission width is wide. Emission width wide. Why emission width means that the color is not pure enough. Okay, so actually, this kind of material is even better. Okay, but the problem of this material is that it's not stable. So if you can come up with this type of material that is stable, Samsung would be very happy to change into this kind of material. Okay, so our goal is try to come up with new material that has better performance but has less side effect. Okay, and one of the things here you see why this is not good, because it has cadmium. Cadmium is toxic, it will be restricted. Okay, but you see this here, it has lead, it's also toxic. Okay, so one of the goals for material scientists is, can we try to replace this lead with a more environmental friendly material, but it still retains the high quantum yield and the pure emission color. That's another goal. So there are many goals we can achieve. Okay, and only one of the goals that is achieved, the industry will be very happy to work with you. Yeah. Okay.
Anyone else? Can I ask?
Yes.
His question is good, like what will be some business ideas related to material. Right now I've seen that natural materials are in abundant state. We have to find lots of mining to get natural materials like diamond.
Natural materials.
So there are the technologies have been upgrading for lab-grown natural materials, like lab-grown diamonds.
Artificial
But
diamond.
it's not an artificial, it's we are
Lab
making
grown,
lab-grown.
But more like
But
natural
it's
diamond.
almost a composition like natural one. What you can say about this?
Yeah, it's possible. Yeah, but usually some of the conditions that makes those natural minerals available will be too expensive for normal lab. For example, if it will cost like more than the price of those diamonds in order to come up with that diamond, then maybe people will not do it. Okay, but one of the goals for material scientists is if you can reduce the cost, then people will be interested. Yeah, because people will can earn money by using the technique. Yeah, so for that kind of research, yeah, there's still people working on that. So, for example, this material usually being researched in solar cells. Okay, actually, silicon solar cell is not the most high efficiency. The most high efficiency solar cell is 3.5, like gallium arsenide. Okay, but the cost is too high. It's too expensive. Okay, so if you can come up with a material that's less expensive but has similar effect, then that will be making a profit. You can make a profit out of it. Yeah, okay, so yeah, if people can come up with something just like natural diamond, but using a low cost technique, yeah, I think that would also become a business. Yeah.
Thank you, Professor. So we thank you very much for your valuable presentation. Thank you, sir. You can write your report. You get more